Okay, this is the last set of 10 questions in the 2014 paper. So next on, I decided to start off with the 2020 paper. And yeah, so since the pattern is a little different from the previous papers, let me just point that out. Okay, so from 2013 to about 2017, the pattern was you had a paper 2 and paper 3 as well. Paper 1 is the general paper that you had. Paper 2 and paper 3 are the physics papers that you have. So what happened from 2018 and you had 2020, 2019 was scraped off because of COVID. So 2018 and 2020, these papers, you just have paper 2 with about 100 questions each. Okay, so I got a couple of suggestions to start from 2020 and go backwards till about 2015. So since we've done 13 and 14, we have to do from 15 onwards. Okay, so I'll be going backwards. So this is the last set of 10 questions that's there in the 2014 paper. Okay, so there was a couple of homework stuff that I gave in the last session, and yeah, a derivation to check up on. So if you want to look at those stuff, you have to join onto the Telegram group that's there. I'll put those things in the description when I upload this onto YouTube. Okay, so now let's get started with this. Okay. Okay. So just okay. So the coming set of questions are like entirely nuclear questions. Okay, so all of this is nuclear physics, and I think that's why it's a better elective to take as compared to others, because a lot of entrance exams questions come from the nuclear part. But this, I think, is mostly the general part of nuclear physics. So you should have covered some amount of elementary particle physics in the general paper. I think that is pretty sufficient for the next set of 10 questions that we're looking at. Okay. So according to the Meson theory of nuclear forces, a neutron emits a pi0 meson and is converted into a proton, emits a pi minus meson and is converted into a neutron, emits a pi plus meson and is converted into a proton, and cannot be converted into a proton. So the idea that you have here is basically the nucleus has neutrons, and it also has protons, right? So what they are basically trying to do, any system that you look at is trying to attain stability, right? Any atom or element that you look at is trying to go to its most stable form that's there in nature. And sometimes what happens is, based on the number of neutrons and protons that's there in the nucleus, based on the stuffiness that's there inside the nucleus, and based on the space or force of repulsion or attraction that's based on there in the nucleus, these neutrons and protons, exchange and convert into each other. So the person who basically proposed this was Yukawa, and it's also called as, theory is in his name as well. So the Meson theory of nuclear forces basically states that neutrons and protons are playing catch-catch. Okay, so how does it play? So the neutron and proton pass mesons to each other, and that's how the neutron gets converted into a proton, and the proton gets converted into a neutron. So that's like the a very, very quick summary of the whole thing. Okay, so let's look at this. So Yukawa's theory of nuclear force, or the Meson theory of nuclear force, it basically tells you that the nuclear force exists as a result of exchange of particles. Okay, so nuclear force that you're talking about is a very strong force, and it cannot be explained by Coulomb's law or any other law that's there. So if you try and do, if you try and do the calculation, the distance between the two particles is about, let's say, 1 Fermi. And if you try and put Coulomb's law, if you try and put the distance R in Coulomb's law to be 1 Fermi, you get a very less amount of force as compared to the force that's actually measured. So nuclear force is pretty strong. And this is basically, why is it so strong? Yukawa said as because it is a result of the exchange of particles between neutrons and protons. So they are continuously emitting and continuously absorbing this particle called pi meson. Okay. So what you now have is, so Mesons are also called as pions. So it's like a short abbreviation that's there. Okay, so when the neutrons and protons are in proximity to one another, they emit or absorb particles. Then this leads to the effect of a force. So the idea is that, let's say a neutron is getting converted into a proton, okay? And what it basically passes is a pi minus meson. What it passes is a pi minus meson. So what you do have here is, okay, a pi plus meson, sorry, a pi plus meson. Okay, so when it's being passed, when these particles are being passed, there is some amount of pushback that's coming, a recoil that comes up. Okay, so a recoil or a change in momentum. Okay, and this change in momentum is what causes the effect of a force. Okay, so that's the reason behind why nuclear forces are so strong. Okay, so he basically posed this question: could it be that the protons and neutrons were playing catch with one another? Okay, that forced them to stay close to each other. So the distance has to be the same. Okay, so that's how they play. If you're further away, it's very hard to pass this pi meson. If you're very close together, then the forces are kind of like not balanced. Okay, so what are the different types of pi mesons? We will come to this in a little bit of a later set of questions that's there in this. So what are the different types of pi mesons? You have pi plus, pi minus, and pi zero. Okay, the neutral mesons that you have. Okay, so let's coming back to this. Oh yeah, let's look at the question now. Since I've described about Meson theory in short, let's look at the question. So according to the Meson theory of nuclear forces, a neutron emits a pi zero meson and is converted into a proton, emits a pi minus meson and is converted into a proton, and emits a pi plus meson and is converted into a proton. So let's look at those equations and how they actually act. Okay, so a proton becomes a neutron. How does a proton become a neutron? It gives out a positive pion. Okay, so basically when the proton is positively charged, okay, so let's intuitively look at it. The proton is positively charged, so it's supposed to emit something positive so that it becomes neutral. Okay, so that it becomes a neutron. Okay, so remember one of these and then work out, just do the opposite. Okay, so remember, ideally what you're supposed to do is remember that proton gets converted into a neutron by giving out something positive. So that should possibly be the pi meson, pi plus meson. And how does a neutron become a proton? A neutron becomes a proton by giving out something negative, right? So that it can get a positive charge, right? So that becomes a pi minus meson. So let's go back and look at this question. They have asked for how does a neutron get converted into a proton. So neutron gets converted into a proton by giving out a pi minus meson, and it is converted into a proton. Okay, so that's option B. Let's move on. Okay, so this is pretty simple. This is something that you've learned in your middle school physics or whatever. Okay, so physics or chemistry for that matter. Okay, so consider alpha, beta, and gamma particles, each having an energy of 1 MeV. Arrange these particles in the order of increasing distance they travel in air. So each of them has an energy of 1 MeV. Okay, each of them has the same energy. If they have different energies, the case is different. But since they have the same energy, this is pretty easy. You know that the most intense of rays is the gamma ray. Okay, and that is possibly going to travel the most largest distance with this amount of energy. Okay, so alpha particles are basically, let's come to this. Alpha particles are basically your helium nuclei. Okay, so they are basically quite heavy as compared to your electrons, which are beta rays, or gamma rays, which are photons. Okay, and beta radiation are fast moving electrons, so they are slightly more penetrating with respect to your alpha particles because they are lighter. And gamma rays are basically photons, so they have the most penetrating power. Okay, and if you want to shield gamma rays, you require lead a lead shielding of like about the order of millimeters. That's like 10 to the power of -3 meters to contain them. Okay, so let's go back to the question and look at it again. Alpha, beta, and gamma particles, each having an energy of 1 MeV, arrange them in the order of increasing distance that they travel. So gamma rays have the most penetrating power, so they're going to travel a lot more distance. So the only way that you can mess up this question is to miss this part, and you arrange it in the order of decreasing. That's the only way that you can mess up stuff. Okay, so don't do that. Just, whenever you have increasing or decreasing stuff, order of increasing or decreasing stuff mentioned in the question, then they have to be a little bit more careful, because I've seen people mess this up the other way around, just because it's not that they don't know the concept, it's just that they weren't careful enough to read it properly. Okay, so that's option D, right? So alpha is heavy, the heaviest. Beta is your electrons, so it's less heavier, and gamma is your photons. Okay, so let's move on to the next one. Okay, so what I have basically done is I've kind of like accompanied a table so that you can use it for any type of radioactive decay. Okay, so remember the table and remember the equations associated with it, so that it's much more easier to solve any type of problem that's associated with beta decay. Okay, so in the beta plus decay, okay, so this is positron decay. The particles accompanying the daughter nucleus are, is it an electron and a neutrino, electron and antineutrino, positron and neutrino, positron and antineutrino? Obviously, you know it's positron. Okay, now you need to remember whether it's neutrino or antineutrino. Okay, so let's take this. Okay, so this is the list of type of decay and the decay equation. So I feel like this is a very easy way to put it into your head, because once you learn it, you can use it for any types of decay that's there. Okay, so your alpha decay basically tells you what? You're getting a helium nuclei out of it. Okay, so you have your atomic mass -4 and your atomic number -2, and you have a helium nucleus that comes out. In your beta minus decay, what's happening? So in your beta minus decay, let's just remember this. The neutron gets converted into proton. This beta can be written as E minus as well. E minus and an antineutrino that's associated with it. Okay, so now when we come to beta plus decay, which is what is mentioned in our question, okay, you have a proton that gives out a neutron plus a positron plus a neutrino. So with your positron, you have a neutrino that's associated with it. Okay, now what you do have is electron capture. Okay, so in your electron capture case, basically what's happening is we discussed this in the last video, I think, last lecture. So what you have is your electron basically gets captured into the nucleus. Okay, so what's it doing? It takes the proton plus an electron, gives out a nucleon, gives out a neutron plus a neutrino. Now, how do you associate this? Okay, so that's the only problem that you have. How do you know it's a neutrino or antineutrino? Because whenever you talk of beta plus decay, positron automatically comes to your head. How do you remember this? So positron, as you know, is a antiparticle. With an antiparticle that you have, always you have a neutrino that's associated with it. Okay, neutrino. So you can have only one antiparticle or one antineutrino. In this case, your electron was just a particle. Okay, so here you have an antineutrino that's associated with it. So basically, you can have only one anti in the equation. Okay, so that's possibly a very good way to remember that. Okay, so now let's go to gamma decay. Gamma decay, basically, there's no change in the atomic number or the mass number because it's a photon, and you don't have any components like your neutron or proton associated with that. And spontaneous fission is another type of fission. Okay, it's basically a chain reaction that is caused by neutrons when they have a sufficient amount of energy. So I just put it up because maybe they would ask you about spontaneous fission, because I see a lot of nuclear questions that are coming up here. Okay, let's move on to the next question here. Okay, so yeah, we didn't discuss this. Okay, so the beta plus decay, the particles accompanying the daughter nucleus are positron and neutrino. Okay, positron is basically your anti-electron. Okay, so you can rule out stuff like when there's two antis or when there is none of them, you don't have those options coming up. Okay, so this is a pretty simple question. Okay, and it's basically based on what we just looked at in the previous slide. So what type of decay is this reaction an example of? Now, if you look at KSET questions, you can only tick one option, but in this particular question, two options are correct. Okay, so they've given marks for either of those. Now, the reaction here, you have a calcium atom, and here you have potassium. So basically, you're getting a decrease in the atomic number by 1. So that is basically associated with beta decay whenever you have a decrease in atomic number by 1. But what is being emitted is a positron. Okay, so let's look at this. It is a beta plus decay or a positron decay. So you have a positron and a neutrino that's emitted out here. Okay, so this is basically how the equation goes. But what you need to note here is that, let's look at this. So beta decay is of two types, right? So you have a positron decay, and you have a negatron decay. Usually they call this negatron decay or the beta minus decay, or they usually have a tendency to typically dub this itself as beta decay. Okay, so many textbooks or many notes that you see, they just go on to say by this particular beta decay or whatever, and they would just assume that it's for beta minus decay. They don't really call this as beta decay, okay, even though it is. So here you have a beta plus decay or a positron decay, and yeah, okay, so that pretty much sums it up. Now what you do see here is that there's beta decay, there's also positron decay. So ideally I would go with this option to be safe, okay, because this is positron decay, and beta decay here is basically of two types, so it's like not so specific. Okay, so because they could probably justify that, you know, because beta decay has, it's a bargain when you tick this option, because beta decay is of two types, and they might be asking you for the specific type of decay. So possibly better thing to do would be to go with positron decay, which is a safe option. But nonetheless, both of these options are correct, because they really haven't, you know, they probably haven't specified that you have to be really specific which type of decay it is. Okay, so now this particular question, okay, if you look at the KSET examinations, you really can't take calculators, okay? So even though this is a very simple question of calculating how much mass is remaining, and they've given you like all the stuff that's there here, this is basically some 10th grade level question, you can't calculate it, okay? So the trick is, how do you go about calculating this thing? Okay, so that's, I tried to develop a trick for it, but I don't know how practical it will be. Okay, so this particular isotope of iodine has a basic half-life of about 8.04 days. Assuming you start with about 1.35 milligrams of the sample, how many milligrams will remain after 13 days? So these are the different options that are given to you. Okay, so let's put these options there, and let's look at, you know, trying to remember basic half-life definitions. So half-life is basically the time required for half of the starting material to decay or change. So remaining mass of the material is basically 1 divided by 2 power n times the original mass, and n is the number of half-lives. So basically n is the time that has passed divided by your half-life. Okay, so now let's look at the problem. Okay, you're given about 8.04 days. The time passed is about 13 days, and the original mass is 1.3 grams. So you need to calculate n. Okay, so the number of half-lives is what you need to calculate. So the intuitive way to do that would be to look at the time that has passed and divide it by the half-life. So the remaining mass is 1 divided by 2 times 2 power n times 1.53 milligrams. And if you have a calculator, this is fine to solve. Okay, so you get 0.499. But what do you do if you don't have a calculator? How do you go about solving this? Okay, so what do we have? We have 1 divided by 2 power 13 divided by 8.04 times, what do we have here? 1.53 milligrams is what we have. Now, what you need to do is, whenever you're looking at exponents, it's going to be hard. Okay, so exponents, try to avoid calculation as much as possible. Okay, because when you try to, and try to come to a closer approximation. Okay, approximations should be approximations you make should be as close as possible, and try to avoid intermediate calculations. So here, if you look at this, 13 can be basically split up as 8 plus 5. Okay, so let's approximate it to 8 plus 4. Okay, so that means if I do a 12 divided by 8, okay, I'm subtracting 1 from here, I get something that's approximately, let's say, 1.5, right? So this is 8, so that's 1, and this is 4, so that's 0.5, right? When I divide it by 8, I get about 1.5. Okay, so let me erase all this, and let me write this as 1.5. 1.5. Okay, 1.5 can also be written as 3 by 2, right? So you have 1 divided by 2 power 3 by 2 times 1.53. And remember, this is the mass that you need to actually find out. Okay, the mass that's remaining. Okay, so this is remaining mass that remains. Okay, so now what you need to do is, let's put this 2 here. Okay, so this is a trick to calculate exponents. I will put this as root 2, and then I would power it as 3. Okay, into 1.53. Now what's root 2? You know what's root 2? But before you do that, don't do 1.414 whole power 3. Make it root 2 times root 2 times root 2. So you end up getting 2 times 1.414. Okay, that becomes 2.828. Okay, so now what you do have is, this value is something that you calculated as 2.828, which is a better thing to do rather than having to calculate this. Okay, the next thing that you could do is, so let me just put this there, and here you have an mass that remains. Okay, I want to calculate what this value is, right? So what do? I want to know, okay, what I will do now is I will take this, put it here, and put this mass remains backwards. So let me just erase all of this. Let me just take a different color because I will be going back to, okay. So what you would have here is 2.8 is equal to 1.53 divided by mass that remains. And why are you doing this? So that's much more easier to calculate the whole thing. Okay, so let me put that aside, and I will erase all of this. Okay, now I will go back to the question so that I can use the options that's mentioned in the question and then try to manipulate this a bit. Okay, so you've got 2.8 is equal to 1.5 divided by mass remains. Now, the idea is that you take each of these options that you have, okay, and you try to calculate if this would figure to about 2.8. So let me just take the first option that's there. Okay, so I do 1.53 divided by 0.835. That's going to give me something like, let's say, 1.8. Okay, way off. If you look at this option that you have 1.53 divided by 0.499, you have about 3.0, which is pretty close to 2.8. Let's look at the other one that you have. Just a second. Okay, so let's look at the other one that you have. This is 1.53, okay, and 0.422, that's going to give you approximately 3.6. And this guy that you have, the last one, you know, if you're looking at this pattern, basically what it's telling you is that the higher or lower the value goes, it's kind of like deviating from this 2.8, right? So 1.53 divided by 0.268, it's approximately, let's say, 5.7. Okay, so the reason why I made it into this form, it's always easier to divide a higher number on top divided by a lower number. Okay, it's always easier to do that. So you could actually like approximate this to 1.6 divided by 8, you know, you get 2 approximately. Okay, you don't have to be so specific, but you can make approximations like this. So it's better to do this rather than having to actually look at the exponent and then be like, oh, now how do I do this calculation and not even attempt this question at all, because this is pretty simple, right? The only issue that comes with this is in calculation. So this is pretty much simple. So it would be a mistake to lose out on this question, in fact, because it's something that's really easy to do, except for the calculations, right? So okay, so now you know that option 2 is pretty close to the result is around 3.0. So you know that it's about 2.8. That's the one with the least difference in values. If you look at other options, the difference in values are like, what's the difference in values for the other options? You have about 1, you have 0.2, you have 0.8, and then you have 2.9. Okay, so these are the difference in options. So you take the one that's least different. Okay, so you take option 2. That's the only way to do it without a calculator. Okay, so that's the best I can come up with. The thing is that the trick, I think, lies in this. Okay, so making an approximation, how do you do this particular calculation? Okay, try to get it in square roots of something that you know, like square root of 3 or square root of 4. If you know the cube roots, you know, like basic cube roots are probably like 2, 3, 5, things like that. And try to express them as something of this form, like with a square root of 2. So then you can do those calculations whenever you have exponents. But remember that don't go ahead and do this, okay? So 13.8.04, don't go and say, okay, approximately 2, because it's going to make a huge difference if you try and do it with 2. You need to approximate it to 0.5 or 0.75 or things like that, okay? Because exponents, when you're dealing with them and when you're trying to do the calculations for exponents, it's going to take a huge amount of time, one, and it's also going to deviate a lot when you're doing the exponent calculations. Even with a small minute difference, there's a huge amount of deviation. Okay, so this is done. Okay, so now let's look at this question. Okay, nuclei above the belt of stability can lower their neutron to proton ratio by beta emission, gamma emission, positron emission, electron capture. So Okay, so how do we go about with this? Basically, when you're looking at atoms, like I told you before, they want to be in the most stable form. So if you have a larger number of, let's say, if you have a larger number of neutrons, okay, if you have a larger number of neutrons, or if in case you have a larger number of protons, there's going to be an issue. Okay, so it's going to try and spit out protons or spit out neutrons so that you can get to your most stable form. Okay, and therefore this neutron to proton ratio is very important in telling you about the stability of the atom. Okay, so let's look at this. Okay, so reasons why there's nuclear instability and why does a nuclear decay to go to the most stable form. Okay, so either there are too many protons. So if there are too many protons in a small container, okay, small space, it's going to repel each other. The other thing is that there's too many neutrons. So there's space issues and it's overcrowded. So it's going to try and spit out neutrons. And the other one is there's too many protons and too many neutrons. So both these factors come in and it results in nuclear instability. Now, elements are unstable because they're basically trying to achieve the perfect ratio of neutrons to protons or protons to neutrons. So the stability is now measured by something called the N by Z ratio, where N is the number of neutrons and Z is the number of protons. And you have a graph for this called the band of stability, which I will show you in the next slide. Okay, so the stable nuclei undergoes radioactive decay to attain stability to form a more stable product, which is called your daughter nucleus. And there is a specific range of N by Z ratio, which is stable. And it's shown in the stability graph, which I will show you in the next slide. Okay, the nucleus does something to basically enter a zone of stability. And what is that something that it does? It's radioactive decay. So different types of radioactive decay lead to the nucleus being inside this region of stability. Okay, so now let's look at this band of stability. Okay, so this particular thing that you see is basically called the band of stability. Okay, so what a new, okay, so let me just tell you about this. This is the number of neutrons that you have. This is the number of protons. Okay, N by Z ratio is what you're looking at. And what it does is, okay, so if you look at something that's there here, it has a larger number of neutrons, okay, and it has a less number of protons. So what it's going to do is it's going to take the number of neutrons that you have, and it's going to decay. It's going to start decaying, it's going to start spitting it out, and it's going to try and reach this band of stability. Okay, so if you look at the band of stability, it's pretty much like N by Z is approximately 1. Okay, so as you go higher, you require higher values of N by Z to about 1, higher fractions of N by Z. So that's about 1.5 and so on. And that's to kind of like balance this. Okay, so there are so many number of neutrons, so you want to somehow balance this, and this happens to be the range in which the N by Z ratios get balanced. Okay, so it has to be about 1.5, 1.4, and so on. So this is the ideal way. But if you look at the lower, the first few elements in the periodic table, first about 18 elements in the periodic table, you realize that the N by Z ratio is almost perfectly equal to 1. Okay, so now let's say if you have another atom with a larger number of protons, okay, what's going to do? It's going to try and convert the number of protons into neutrons, okay. It's going to do this beta decay process that's there, and it's going to try and reach the most stable region, okay, or the band of stability. If you have something that's there here, okay, if you have an atom that's there here, it has both larger number of protons as well as neutrons, and what it's going to try to do is try to come to the stability by expelling as much neutrons and as much protons as possible using alpha decay. Okay, so something's above, like really high, probably above lead. Almost all of them are radioactive, and you don't find any other stable isotopes for those radioactive elements. Okay, all of them go through gamma emissions. Okay, so now let's look at this again. Let's go back and look at the question. nuclei above the belt of stability can lower the neutron to proton ratio by beta emission, gamma emission, positron emission, and neutron capture. So when you go back and look at this graph, nuclei above the band of stability basically are here, right? So, yeah. So nuclei above the band of stability are here. That means they have more number of neutrons. If they have more number of neutrons, they are going to spit out electrons so that they can form protons and enter the band of stability and lower their n by z ratio. Okay, so what does that basically do? That's beta minus decay. Okay, in the case of your lower, this is what's given in the question. Okay, so this is what is asked for in the question, and that's beta decay. Now, in the case where the number of protons are more, it's below the band of stability, so they will try to go into the band of stability by doing what? They will try to go into the band of stability by decreasing the number of protons they have, converting them into neutrons, and again increase the n by z ratio that they have. If they have more number of protons and neutrons, they will try to expel both of them using alpha decay. Okay, so this is about this question. Let's just look at that. That's, yeah. So this can lower the neutron to proton ratio by beta emission. Okay, so now let's look at, yes. Okay, so how many neutrons are emitted when a californium-249 nucleus, Z is equal to 86, is bombarded with a carbon-12 nucleus to produce this particular type of nucleus? So now let's look at the different options that there are. So it's basically what you have to do is you have 249 CF, and this is 98. Plus a carbon-12. So carbon-12 is having an atomic number of 6 to produce some particular, let's look at, yeah. So how many neutrons are produced? So neutrons are basically written this way. Okay, so X number of neutrons are produced, and you have 257 out of 104. So this is how the equation goes. Okay, it's pretty simple. This is again straightforward, something that's probably done in each standard. Okay, so yeah, so your idea here is to find X, and how do you do that? You have to do X times 1 plus 256. 257 is equal to 12 plus 490. 249, sorry. So 249 plus 12 is equal to 257 plus X times 1. And when you calculate this, X turns out to be 4. So that's option D. Okay, so let's come to this question. In the case of a fundamental particle, what are the following that's observed? Okay, so you need to select the correct option from here. Conservation of energy is obeyed, conservation of momentum is obeyed, but angular momentum is not obeyed. Conservation of parity is not obeyed. Conservation of isotropic spin is obeyed. Okay, so what I'm going to do is I'm going to show you the different conservation laws, not go into each of these terminologies in detail, but I will tell you a little bit about them. Okay, so that you can understand, so that it's possibly even helpful for your third semester exams that are going to come up. Okay, this is a part of general paper. So now they've given this as option D, okay, but it's a wrong option. It's not correct. Let's just explore and understand this a little bit further. Okay, so there are certain universally observed quantities. So this has to be obeyed by elementary particle interactions. Okay, what are we talking about in the question? We're talking about fundamental particles. Okay, elementary particle interactions. So let's look at this. Okay, so universally conserved quantities are basically conservation of momentum, conservation of energy, conservation of angular momentum, and conservation of charge. So these are universally conserved quantities, and this has to be obeyed even in the case of elementary particle interactions. Now, there are certain conservation laws that are specific to elementary particle interactions. What are they? They are conservation of baryon number, conservation of lepton quantum numbers like Le, L mu, and L tau. Okay, you should have learned them in your general paper, elementary particle physics. Okay, and strangeness. Okay, and there are isospin and parity. Okay, so now let's go back to this. Okay, so what are your lepton quantum numbers? This is your electron lepton number. This is your muon lepton number. This is your tau lepton number. There are three families of leptons. These are first generation, second generation, and third generation. Okay, baryon number is specific to your baryons. Okay, so I will show you the detailed classification on the next slide that we have. Okay, and strangeness. Okay, so strangeness is basically coming from the fact that some particular hadrons, which are particles that are strongly interacting. Okay, so hadrons are strongly interacting particles. Some particles that are there in the category of hadrons do not undergo decay via strong interactions. Okay, so that's like very strange, and therefore it's called strangeness. The quantum number that's associated with that is called a strangeness. I'm not going to go into detail on that because that itself is like an entire semester's work. So let's just look at this. So this conservation law is absolute only for strong interactions in electromagnetic processes. It may be violated in processes which are under the weak interaction, which undergo via the weak interaction. The next thing that you have is something called as the isospin. So yeah, so if you look at the nucleons that there are in the nucleus, they are quite similar. The proton and neutron are quite similar. So the way that you write them is using an isospin operator called I hat. Okay, so the way that you write them is using an isospin operator called I hat, and each of these has three quantities. You have an I1, you have an I2, and you have an I3. Okay, and this is mostly used in case I3 is the one that's mostly used to look into various other conservation laws and calculations that you have. Okay, so now let's just look at a general notation of, general analogy of isospin. Okay, so here you have a proton. Okay, and what you can say is that it's an isospin up. It's analogous to your angular momentum. Okay, so if you look at angular momentum, you have about three components there. Here too, you have about three components. Now the next one that you have is a neutron. Okay, and you have an isospin down. That's how it's denoted. Okay, so that's just a very quick summary of your isospin and what it basically indicates. So here you have conservation of isospin. When and how is isospin conserved? It's conserved only for strong interactions. That means conservation of isospin is not universal. Conservation of strangeness is not universal. Okay, these quantities are specific. Conservation for baryon number and lepton number are specific to family particle, is specific to elementary particle interactions. And now what's the last one that you have? You have, so you have parity, and parity, there is a very famous experiment that you've done in the second semester, which states that parity is not conserved for weak interactions. Okay, so there's parity, violation, and weak interactions. Now, let's go back, okay? Before I talk about anything more, let's go back and look at this, okay? So, conservation of momentum, conservation of energy is obeyed. This is correct, okay? Conservation of momentum is obeyed. This is correct, but angular momentum is not obeyed. That is not correct. Angular momentum is obeyed, okay? Conservation of parity is not obeyed. That statement is correct. Okay, let's look at it in terms of true or false. Whenever you have several statements, mark them as true, mark them as false, and then go ahead and do it. Okay, so conservation of parity is not obeyed is correct. Okay, because if you look at weak interactions, parity is not conserved. Conservation of isotropic spin is obeyed. So is that correct? No, it's not correct. If you look at the case of weak interactions, isotropic spin is, sorry, let me just erase that. Okay, I can't erase that. Okay, yeah. So conservation of isotropic spin is obeyed. Is that correct? If you look at the next slide, let's just go and look at the next slide. Let's just go and look at this. So what do you see? Conservation of isospin, it's only conserved for strong interactions and not for weak interactions. So that is wrong as well. Okay, so which ones are correct? Okay, this only half of it is correct. This half of it is wrong. Okay, so 1 and 3 are correct. Do you see options 1 and 3 here? No. Okay, so this probably should have been challenged, and this is I think the options here, which is given in the answer key, are wrong. Okay, it's not option D. Okay, even though option D looks close, because when you're looking at isospin, they do say that it's conserved for strong interactions, but it's not conserved for the others. That's that. Okay, so now there are a few things that I'd like to point out before for the purposes of the next set of questions that we might come across in nuclear physics. I would like to give you some small ideas behind it, and possibly if you're in the third semester, you should have kind of already looked into these. Okay, so let me just go back and create some space. Yeah. Okay, so the first thing that I want to tell you is that this is something that's known from your 12th standard. There are 4 types of interactions that you have. What are they? You have strong interactions, you have electromagnetic interactions, you have weak interactions, and you have gravitational interactions. Okay, so these are the 4 types of interactions that you have. Point number 2 that I would like to state is that electrons and muons and their associated antiparticles cannot interact strongly. Okay, cannot interact strongly. The next thing that I want to say is protons, neutrons, and pions, or Pimazones. They're also called as Pimazones. We just came that across. Pimazones, pi 0, pi plus, pi minus, can interact strongly and are called hadrons. What are they called? They're called hadrons. Okay. The next thing that I would like to show you, okay, so these are 3 points that we have. Another statement, weak interactions are responsible for beta decay. Beta decay. Okay, so again, an example of the beta decay that we've been talking about so far is neutron becomes a proton. You have an electron and an anti-neutrino that's associated with the electron. Then what I would like to talk about is this last point, massless electrically neutral particles which have spin-off are neutrinos. Okay, so neutrinos are spin-half particles. Okay, they are spin-half particles and they are massless. And what? They are electrically neutral. They do not have charge, neutral. Okay, so these are some kind of points that I've stated here. Now, it's very hard to remember some of them. So let's just look at this table right here. Okay, so let's look at the classification of particles. Okay, so here they are strongly interacting particles, and these are called as hadrons. And you have leptons, which are weak or electromagnetic interactions. Okay, which are associated with weak or electromagnetic interactions. Then you have 2 types of hadrons. One is called the baryons, okay, fermions, and the other one's called the mesons or the bosons. Fermions have the property of half-odd integral spin. Okay, you've got a proton and neutron which have spin half. Okay, so remember, proton and neutron always have spin off. They're constituents in the nucleus and they have spin half. The next one that we have is mesons or bosons, which have integral spin, and they include zero spin as well. So the Pimazones or pions that we were talking about have spin 0. And these are the different types of leptons that we have. You have an electron, you have a muon, and you have a tau. So associated with each of these, you have an electron lepton number, you have a muon lepton number, and you have a tau lepton number. And they're associated neutrinos. Okay. So that's something to, like, keep in your memory. It's not really associated with the question that we were talking about that involve conservation laws, but this is to know and understand what particles you're talking about, what category electrons come into, what category protons or neutrons come into, and what category Mesons come into. Okay. So let's look at the next question. Okay. This question has incomplete data. Okay. So what I have done is I've found the right question for this, and we're going to try and try and do that particular question. Okay, so I'll tell you what's missing here. The decay chain of the radioactive nucleus, they haven't specified what radioactive nucleus. Okay, so it's basically like going from nowhere and doing 8 alpha decays and 6 beta decays. The final nucleus at the end process will have what? Okay, so now let's look at let's look at this. Okay, the decay chain of the radioactive nucleus involves 8 alpha decays, 6 beta decays. The final nucleus at the end of the process will have what? Okay, so now what do you mean when you're getting an alpha particle that's emitted? You need to decrease the atomic number by 2 and decrease the mass number by 4. When you're talking about a beta particle, you increase the atomic number by 2 and the atomic mass is atomic number by 1, and atomic mass is unaffected. Okay, so this is how the reaction goes. Okay, this is the nucleus that this should have given, uranium-238. Okay, and here you have to undergo 8 alpha decays. Okay, so you need 8 helium nuclei that's coming out, and you need to have 6 beta decays. Okay, so that's 6 minus 1. So now how do we write that down? After about emitting 8 alpha particles and 6 beta particles, the Z value of this is going to be 92 minus 8 2s are 16. 8 2s are 16. Okay, and then you have a plus 6 because this is a beta particle. Okay, so let's just write that down. 92 is equal to 8 into 2 minus 6 plus Z. So that's about 238 for the, that's about, let's just clear all of this. That's about 82 for your Z once you finish calculation. And this is about, when you do the same thing for the top part, so that's 238 is equal to 8 times 4 plus 0 plus A. So you find out A to be equal to 206. Okay, so this is just simple calculation, very simple problem. Again, something that you might have done in middle school. Okay, so now, so we come to the last question that we have. Okay, so CPT. CPT is basically charge operator, parity operator, and this is time reversal operator. Okay, so what they're asking you here is not about the specificities of CPT, but basically who invented this, who formulated this theorem. So, okay, so CPT theorem is also known as Ludus-Pauli theorem, Rayleigh-Wigner theorem, optical theorem, Gelman theorem. So these are the different things that are there. To just give you a story about the CPT theorem, okay, so in the formulation of your quantum field theory, it can be shown that it's impossible to violate CPT, that is your operations of charge, parity, and time reversal, without drastically altering this theory. Okay, so because you cannot violate CPT without altering this, it's considered to be, like the reactions that we talk about are considered to be CPT invariant. And there is a consequence of this particular CPT invariance that you have, which we will talk on the last point in this slide. So the fact that a wide class of quantum field theories is invariant under CPT was demonstrated by G. Ludus and Wolfgang Pauli. So that's why it's called the Ludus-Pauli theorem as well. Now, who physically looked into this? Okay, looked at the experimental part of this or the physical consequences of your CPT theorem. This is done by Chinese physicists Li and Yang. And what is the implication that CPT has? Okay, so CPT, you have charge, parity, and time. Okay, so because of this particular theorem, every particle has the same mass and same lifetime as that of the antiparticle. This is the main consequence of this, one of the physical consequences of the CPT theorem. Okay, so that concludes this session. So the next lecture will be for the 2020 paper. Okay.